Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 5, Lesson 1, the absolute value function. So going back to Topic 3 where we learned about linear functions, remember what a domain is and what range is. Now we're going to apply those definitions as well as transformations of linear functions. We're going to apply those rules to the absolute value function. For the explore and reason, we have this diagram. And we have groups of students hiking from these mile markers. Looks like they're mile markers probably from this part of the road over here on the left. And the waterfall is at mile 5. And we want to determine how many miles each hiker has to get to the waterfall. So we can think of the waterfall being at point 0. And so the person at mile 6 is how far away from the waterfall? Well, they're 1 mile away. The distance is 1. What about the person at mile 8? They are a distance of 3 miles from mile 5. And the person at mile 2 is also 3 miles, but they are in the opposite direction. They're to the left. So if we think of this like a number line, we could draw a graph where 5 is at the center, it's our 0, and 6 is 1 unit away, 8 is 3 units to the right, and 2 is 3 units to the left. But as we're measuring distance, we can't have negative numbers, so we're just going to talk about the absolute value or the distance from 0, or the distance from the waterfall. So let's look at the absolute value function and the key features of the graph. So back to function notation, remember f of x is the same as y. Okay, this is my output. I'm going to just review. This is my output, and x is the input. So if we make a table for this function, it's good to use numbers a little bit to the left of 0 and then a little bit to the right of 0 for our input, because we're talking about absolute value, so we want to go a little bit to the left of 0, a little bit to the right. And when we plug in our input into the function rule, all we do is take the absolute value, which is just make it positive, because distance is always positive. And then we're going to write our points for the graph as input, comma, output. We're used to seeing it x, comma, y. When we use function notation, we will see it as x, our input, comma, f of x, our output. So instead of y, we're just going to write f of x. So here's our ordered pairs, -2, comma 2, -1, comma 1, etc. And if we plot those points, we can see we get this nice V-shaped graph. It's symmetrical. It's decreasing or has a downward slope on the left, and then it's increasing or has an upward slope on the right. So since it's symmetrical, we have what is called an axis of symmetry. For the parent function, which is f of x equals absolute value of x, this is just the basic home function called the parent function. We start at 0, and then we have a v, an upward facing v. So our axis of symmetry is at 0. And our vertex, it's the point where we change directions. The vertex is the point where we change directions. That will always be on the axis of symmetry. So remember, your vertex will always be on the axis of symmetry. So then let's talk about the domain and range of our parent function for the absolute value. Here, I've copied the graph again. Remember, domain is our inputs or our possible values for x. And our range is output, or our possible values for f of x. So for our input, what are the possible values for any x's, any of our inputs? Well, we have arrows on the end of our graph, so it goes on and on to the left and on to the right. So our domain is going to be all real numbers. What about our range? We do have a limit. It does not go below 0. So our range is going to be, we can write y. Y is going to be greater than or equal to 0. Any value there. It can be a decimal, be a whole number, but it has to be equal to or greater than 0. So how about a transformation of our parent function? Now we're going to look at g of x, and all we're doing is we're taking the absolute value of the input and then we double it. So if we remember our transformation rules, we have a scale factor on the outside of the parentheses. So we are changing the output. We're changing the output since it's on the outside of the parentheses. You can think of the absolute value lines as special parentheses. So if we take the input and then we take the absolute value or make it positive and then double it, our output should be greater. Our y values should be greater. So let's take a look. Where x equals 2. For our parent function, our output would be positive 2. But if we double that, then our output for g of x would be 4. So we can see that this is a vertical stretch. We're taking the output and stretching it vertically, so it is more narrow. The v is still upward facing, but now it's more narrow since we have that scale factor in front of the input. We're multiplying the whole output by 2. The domain is still going to be all real numbers. We still have arrows on the end of our graph. And the output, or the range, is still going to be greater than or equal to 0. We haven't changed that. We only have positive values because absolute value can only be positive. Here's another transformation. Now we are taking our input, and after we do the absolute value, then we multiply it by -1. So we're really just doing the opposite of the absolute value. So instead of having only positive values, now we're going to have negative values. So what we have done is we have inverted or flipped our graph. So now instead of being an upward facing v, when we have a negative scale factor, if we're multiplying by a negative number, that's telling us we are flipping the graph. So now it's going to be downward facing. Okay, so negative scale factor, if we're multiplying by negative outside the parentheses, we are changing from upward facing to downward facing. The domain, we still have arrows on the end of our graph, so the domain is still all real numbers. But now the range has changed. Now the range is going to be less than or equal to 0. All of our possible y values for h of x are going to be less than or equal to 0. Notice also that we have a change in direction. So our rate of change is increasing, and then when we get to the axis of symmetry, then it changes direction, and now our rate of change, or our slope, is negative. It's decreasing. Try it number 2. Describe how the domain, the range, and the intervals where they're positive or negative compare to the parent function. Okay, so our parent function, we know, looks like an upward facing v. G of x, we have a scale factor on the outside of the parentheses, so we are changing the output, but this time our scale factor is less than 1, so we are making our outputs smaller. That means we are compressing our graph. So our graph is going to be wider for g of x. Okay, so g of x, we're going to vertically compress our parent function. There's still arrows on the end, so our domain is still going to be all real numbers. So we could use negative infinity to positive infinity, bracket notation. We could then also say that the range is going to be everything greater than or equal to 0 because it's still upward facing. And the intervals where they are positive, well, we're positive when we are greater than or equal to 0, and it is decreasing, or our slope is negative, when the input is less than or equal to 0. How about h of x? Let's do this one in pink. So now we have a scale factor that is negative. That means we are going to flip it, and we're also doubling it. So it's a vertical stretch, so it's still going to be narrower, but it's also going to be reflected across the x-axis. So now it's going to be downward facing. Here's h of x. The domain is still going to be all real numbers, so I'm going to show you an interval notation, negative infinity to positive infinity. The range now is less than or equal to 0, because only negative values, and it is increasing, or it is positive now when it is less than or equal to 0. So now my positive slope is when it's less than 0, and it is going to be decreasing or have a negative slope now when x is greater than or equal to 0. So notice what changed when we have a downward facing absolute value. The domain still stays all real numbers, but the range and the intervals for positive and negative changes. Example 3, let's do an application problem. Jay rides in a boat from his home to his friend's home in a neighboring state. The graph of the function d of t equals 30 times the absolute value of t minus 1.5 shows the distance of the boat from the state line. So that's important. We're going from the state line. Distance from the state line. So that means at 0, we are at the state line. We have 0 distance from the state line. And the output is measuring the distance from the state line, and then the input is measuring time in hours. So we can see how long does it take him to reach the state line? Well, at 0 distance, it takes him 1.5 hours. So it takes him 1.5 hours to get to the border. And then where is it decreasing? Well, it's decreasing when it's less than 1.5. So here it's decreasing. That means the distance is decreasing. We're getting closer and closer to the state line. And then our graph is increasing, or we're getting farther and farther away when the input is greater than 1.5. We're using input notation. So when we're talking about intervals, we're talking about the input values. What intervals of the input will it be increasing? Well, greater than 1.5 and up to 3. You can see we don't have arrows on the graph, so we don't keep going on forever and ever. So make sure it's not equal to. It's just up to 3. How far away is it to the border? We know it takes 1.5 hours, but can we determine how far away it is to get to the state line? Well, yes. We have an initial value. We have an initial distance at 45. So it's 45 miles to get to the state line. And then, but what's he doing? He's getting closer to the state line, and then he goes another 45 miles to get to his friend's house. So he travels a total of 90 miles, 45 miles to get to the border, 45 miles to get to his friend's house. It takes him 1.5 hours to get to the state line, and then a total of 3 hours to get to his friend's house. How does the graph show the domain and range of the function? Well, we talked about that. The domain is going to be our input values. So just from 0 hours to 3 hours, because it takes him a total of 3 hours to get there. And the range, remember, the output is going to talk about the distance traveled from the state line, not total distance. So distance from the state line. So the maximum distance he is 45 miles from the state line. He's 45 miles on one side of the state line and then 45 miles past the state line. So that's why our values are from 0 to 45. The total distance traveled is 90, but he goes 45 miles to the border and then 45 miles past 0, if you will. So remember, the graph is not, he didn't travel in a V, that was distance to the border. Try it. Number 3, a cyclist is competing in a race and rides past a water station. The graph, d of t, shows her distance from the water station. So from the water station, that means 0 is going to represent the water station. And t represents minutes, and the output, d of t, is the distance in kilometers. So how long does it take her to get to the water station? It takes her 60 minutes to get there. How far away is she? So we could say 60 minutes to get to the water station. How far away is it? Well, let's look at the total distance. The maximum distance is 20. So she's 20 kilometers away at the start. What does the graph tell you about her race? Do we know the total distance she travels? Yes, we do. We know the total distance she travels. She travels 20 kilometers to get to the water station and then another 20 to finish the race. So her total distance then is going to be 40 kilometers. And how about the total time? We know it took 60 minutes to get to the water station, and then she goes another 60 minutes to finish the race. We can see the water station is really at the axis of symmetry, right in the middle. Example 4, rate of change. So this is important to remember. When they're asking about rate of change over an interval, they're talking about the input values, okay? Rate of change for the input. Rate of change is another word for slope, so we need to be calculating the slope. Remember slope formula? Change in y over the change of x. I also like to write it triangle or delta y over delta x. The triangle means change. So we're finding the rate of change between 2 points on the input. Okay, so be careful because they tell you what axis to look at there. We're looking at the t-axis, not d of t. Which section is, or what is the rate of change for this section? From 2, so that's our starting point. Our first value is at 2, and going up to 2.5. There's our starting points. And we can find the rate of change by looking at those 2 points. So just write the ordered pairs, 2, 15, and the other pair is 2.5, 30. Plug that into our slope formula. 30 minus 15 over 2.5 minus 2. We have a slope or a rate of change of 30. Now it's positive. Does this make sense? Is this an upward facing slope or an upward climbing slope? Yes, it is a positive slope. What if I was asking about an interval over here, like from these 2 points? From 0.5 to 1 hour. Well, it looks like it's going to be the same slope, same value, but it would be negative because we're getting closer to the state line. So our distance is decreasing. So when you're calculating rates of change, make sure you're looking at the intervals for the inputs. And just use your slope formula. Try it number 4. Kata gets on a moving walkway at the airport. Then 8 seconds after she gets on, she taps Lisa. So this graph is showing the distance to Lisa. So here's Lisa at 0. She gets to Lisa at 8 seconds. Calculate the rate of change in her distance from Lisa from 6 to 8 seconds and then from 8 to 12 seconds. So if we zoom in and look at our intervals, here's 6. We are not exactly on the grid, so we can't get an accurate data point right there. We know our second point is going to be 8, 0. But if I notice, this is a linear graph. It's got a constant rate of change. So can I find a different point to use to calculate my slope and it will be the same? Yes, it will. So let's use this point up here, the starting point, because it will have the same rate of change. So that point is going to be 0, 20. And then for the next part, where she is getting farther away, we're going to do 8, 0 again. That's our first point. And if we look at 12 seconds, again, not an accurate point to use for slope. So let's use a different one. I like this one right here. Let's use that point, 16, 20. So our second point would be 16, 20. So we have 2 rates of change to calculate, or 2 slopes to calculate. Let's do the first one. 0 minus 20 over 8 minus 0 is negative 20 over 8. That is negative 2.5. Does it make sense that we have a negative slope? Yes, we are decreasing our distance. We're getting closer to Lisa. For the next interval, remember, I can use a different point because it's a constant rate of change. So I can use a different point that gives me an accurate ordered pair. My first point is 8, 0. So we're going to have 20 minus 0 over 16 minus 8. We have 20 over 8. So now that's a positive 2.5. Does it make sense that it's going to be positive? Yes. And you can see the slope is the same, just opposite signs. Remember, if we have an absolute value function, it is symmetrical. That means the rates of change should be equal in magnitude, just opposite signs. So same value, just opposite signs on either side of the axis of symmetry. We made it to the concept summary for absolute value functions. Remember, this is your parent function, so be able to recognize what the parent function looks like in a graph. Remember your axis of symmetry. Your vertex is going to be on the axis of symmetry. This will be important when we start to do more transformations with absolute value functions. The domain, all real numbers, it goes on and on to the left and to the right. Possible output or range values, it's just upward facing, so only positive values. If you have any questions, put them in the comments. Make sure to like and subscribe and come back for lesson 2.